Well, we looked at heat in our last lesson. Now we're going to look at quantifying work, how to calculate a value for work if it's given to us. So this is a continuation of the same section. We're going to be looking at a specific type of work that we call PV work, or pressure volume work. We maybe some class in your past, it's not something we've talked about in here, that work can be determined by force times distance. Force against an object and pushing it across a certain distance is a classic physics definition of work. Well, if we are dealing with gases and we're going to have a chemical reaction that's going to do work, the only way that chemical reaction is going to do work is if it has a gas expanding, or it might have a push in and a gas contracting, okay? So whenever that happens, it can be defined as this equation, okay? So what's it pushing against? It's pushing against an external pressure. And so that's kind of a measurement of that force. Its distance to push is how much bigger it expands or how it gets contracted. And so volume helps us measure that. So pressure times a change in volume is a way of determining work, and that is going to be the equation that you need to hold on to. So you had an equation for heat, mc sub s delta T. Now you have an equation for work, minus P delta V. Now let's think about that minus sign. Well, first of all, this is called PV work, like I said. Pressure volume work, but I always call it PV work, and it only happens when a gas expands or contracts. And if a chemical reaction does work, it's because gas is being produced and expanding, or a gas is being consumed and it's decreasing in size. Pressure, the external pressure, it's a constant pressure that this reaction is being surrounded by. So if it's pushing out and it's a pressure of some sort, then that's what the P stands for. So we've defined all of our terms in this equation. So if we look at this equation and we plug in our typical gas units, okay, if we were doing PV equals nRT, we'd have specific gas units. What would be the units that work would be in this equation? Think about that. Well, pressure, atmospheres, volume, liters, okay? So we call it a liter atmosphere, not an atmosphere liter for some reason. I don't know why, but it's a liter atmosphere. Liter atmosphere is an energy unit. It's a weird energy unit, and it's not an SI energy unit. So what we want to do is take it out of this liter atmosphere realm and put it in a joule realm. When we do that, here is the conversion. And this is a conversion that you need to know. It's not provided for you on the periodic table when you take the exam. A liter atmosphere is 101.3 joules. Now, there is a roundabout way to get this conversion if you look at the periodic table, and I'll talk to you about that in class. If I forget to do so, somebody ask me about it, because I want to show you how you could manipulate a few things on that periodic table that I give you in order to come up with this in case you forget it. But 101.3 is that relationship between the two. Okay, so let's just get a visual image in our mind about this process taking place. On the left-hand side, we have a gas in a cylinder. This would be like in the engine of your car, okay? There's a certain volume of gas in there, and the piston is pushing down. Now what happens is, for your typical gasoline engine, is there's a spark inside of there. That spark makes an explosion. Chemical reaction takes place, and there's an expansion that takes place. That expansion would give us a change in volume against that pressure that was already pushing down, and so we do final minus initial. So let's think about the sign for just a minute. In this expansion, would the delta V be positive or would it be negative? All right, let's go back to our light board here and let's think about these signs. For delta V, would that be positive or negative for that picture? Well, it's expanding. Final minus initial, big number minus a little number, this would be a positive value. Then we think about what's happening in terms of the sign of work. Work is a negative P delta V. Well, this is positive. It's always got to be pushing against a pressure that's positive. There's no such thing as a negative pressure. So the work would be a negative value. So this equation is my easiest way for some reason, because I have the equation memorized, my easiest way to keep sign convention. If it's expanding, pushing out, that's a negative work. Now, we learned earlier to think about work is always negative if you're pushing against an external pressure. When you're doing that, the system is losing energy, the work is negative, and so we had a sign relationship with that. Now we see that sign relationship playing out here with the equation, and it's easier for me to hold on to this equation mathematically and think about the sign convention. Expansion is always a negative work. Okay, so I have a certain gas. We'll work this problem here and use this equation we see. And it is expanding, and it's expanding against a pressure that's 0 atmospheres. Well, think about it. You're pushing against nothing. If you're pushing against nothing, are you doing any work? That would be a 0 value. But it shows up as a 0 value if you plug our numbers in, okay? So we put a 0, and that is atmospheres. It doesn't matter what unit it is. 0 is 0. And it's pushing a change in volume from 0.5 up to 2.5. So final minus the initial, and that's both in liters, and that is going to give me no work, okay? So work is 0. But I want you to do it when you're actually doing work. So I just want you to hold on to that notion. You've got to be pushing against that pressure for there to be any work. If you're expanding into a vacuum, no work involved there. But here we have a situation where we are pushing against 1 atmosphere. I want you to pause, and I want you to come up with the answer. Select your answer for this one, and then resume. Let's see if you got it right. Well, if you got a negative 203 joules, you're correct. Common mistakes is not to think about joules, but I didn't give you that as one of the possible answers. So we're not putting it against 0 atmospheres, we're putting it against 1 atmosphere. We're doing final minus initial, and that's going to give me a negative 2.0 liter atmospheres. The final thing you really ought to do is convert that to joules. So we don't want liter atmospheres, we want joules. And it takes 101.3 joules to equal a liter atmosphere. And to 2 significant figures, well, that's 3, okay? And really, we can only know it to 2, so a negative 2, well, how would we do that? A negative 2.0 times 10 to the 2 joules would be the way to describe that with 2 significant figures. Okay, so let's do some tie together here, okay? We're going to look back and review that first law of thermodynamics, and we're going to apply stuff that we have learned at this point into this equation. All right, here we have a reaction. We're going to apply this statement to what we know. All right, in this reaction, we're starting with some sodium metal, and we are reacting it with some water. So we're dropping a piece of sodium metal into water, and this reaction takes place. The sodium hydroxide is soluble in the water, and we're producing some gas. That's the key to working this problem. So in the course of doing this reaction, it is producing a gas. And it also tells me something about the heat. It gives off heat. So stop the video, choose your response, and then resume. All right, did you say that they're both positive? If you did, you'd be wrong because I've got the star in the wrong place. Let's go and let's fix what it really should be, all right? So if it gives off, oh no, it does say negative. Gosh, I just lost my mind there. Okay, so the Q and the W are both negative. Then you'd be right, just like I was when I created this slide. Okay, so why is the Q negative? It says it gives off heat. If it's giving off heat, then that is a negative value. If it's expanding, okay, if it's expanding, look at this again, if this is positive, then the work is also going to, is going to be negative. So we have got 2 of those being negative, both the heat and the work. All right, now if we know both the heat and the work are negative, can we determine a sign for delta E? I want you to look at those choices, and I want you to stop the video and choose one, and then resume when you've got something in your mind. Well, in this case, yes, you can know, because we know the equation, and let me write the equation down here for delta E. Delta E equals Q plus W. Now we've established in this reaction that Q was negative. Okay, it's a negative sign. We have a value of work that's negative. So if you're taking a negative and adding a negative, delta E is going to be negative. It doesn't matter what size these are, your change in internal energy is going to be negative. That means that system is losing total energy. It's losing it in two ways. It's giving off heat and it's doing work on the surroundings. So the change in internal energy of the system is getting negative. Where is that energy going? Into the surroundings. Where is the heat going? Into the surroundings. What's happening with the work? The system is doing work on the surroundings. And that's going to make the total energy of the system decrease, and that would give us a negative value for that. Okay, so that ends our discussion of tying together our heat and our work, where we went through this video and we learned all about work and how to calculate work and then tied it together with our first law of thermodynamics.